Suppose p is prime and phi of p is the product of powers of primes. We prove there exists some element with order pi to the ni, and that the product of these xi's is going to be a primitive root. So we've proved there's at least one primitive root. Could there be more? Suppose A is a primitive root mod p, where p is an odd prime. This means that the values corresponding to the powers of A are distinct mod p. Now consider a to the k and the values. How many distinct values are there in this sequence? So remember, concrete doesn't hurt. So if we take mod 7, our primitive root is going to satisfy. If we consider the powers of a squared, we get, and there's only 3 distinct values. But if we consider the powers of a to the 5th, we find a to the 5th squared, a to the 5th cubed, and so on. So in some cases we got a full set of the powers of a, and in some cases we didn't. And the thing to notice is the greatest common divisor of 2 and 6 is not 1, but the greatest common divisor of 5 and 6 is 1. So remember, relatively prime is almost as good as prime. So suppose k is relatively prime to p minus 1. Consider the sequence of terms. If 2 of the terms are the same mod p, then we have p divides their difference. So we can factor out that a to the mk, and since p is prime, that means p either divides a or p divides. But p can't divide a, so p has to divide a to some power minus 1. So a to the power k n minus m must be congruent to 1 mod p. Now, since a is assumed to be a primitive root, that means this has to be a multiple of p minus 1. But since we've assumed the greatest common divisor of k and p minus 1 is 1, then every prime factor of p minus 1 must also be a factor of n minus m, which means n minus m has to be a multiple of p minus 1. But since n and m are both less than p minus 1, this can't happen. Consequently, if the greatest common divisor of k and p minus 1 is 1, then all terms in the sequence of powers of k are distinct. Since there are p minus 1 phi of p terms, then a of k is another primitive root mod p. And since the only requirement is the greatest common divisor of k and p minus 1 is 1, then every k relatively prime to p minus 1 corresponds to a primitive root. And there are phi of p minus 1 such values of k. Consequently, if p is an odd prime, there are at least phi of p minus 1 primitive roots mod p. At this point, the question to ask is, could there be even more primitive roots? Suppose b is another primitive root. Since a is primitive, there's some power k where a to the power k is congruent to b. If the greatest common divisor of k and p minus 1 is 1, then b is one of the primitive roots we've already found. So let's suppose that greatest common divisor is d, where d is greater than 1. Then there exists k prime and m, where k is dk prime, and p minus 1 is d times m. Then we know that a to the power k is congruent to b, so that's a to the power dk prime, raising both sides to the power m, and rearranging. Since dm is p minus 1, that gives us, and since a to the power p minus 1 is always congruent to 1, we have, and so that tells us that b has order m, which is less than phi of p. But it was supposed to be a primitive root, so this is impossible. Consequently, if a is a primitive root mod p, then all primitive roots must have the form a to power k, where the greatest common divisor of k and p minus 1 is 1. This means that k is a number relatively prime to p minus 1, so there must be exactly phi of p minus 1 primitive roots. For example, let's try to find all primitive roots mod 37. We note that phi of 37 is 36, and we find that 5 is a primitive root. Since 5 has order 36, then 5 to the k, where the greatest common divisor of k and 36 is 1, will also be primitive. We note that phi of 36 is 12, and the numbers less than 36 that are relatively prime to 36 are, and so the primitive roots will be 5 raised to each of these powers. And we find, which is our list of primitive roots.